Welcome to Future Talk. On today's program, we're going to talk about some of the latest frontiers in space exploration. I have two guests from NASA's Ames Research Center. William Borucki is the chief scientist and driving force behind the Kepler mission, whose purpose is to search for Earth-like planets in other solar systems. And Anthony Colapret is the top scientist and leading inspiration of the L-Cross project, which recently discovered water on the Moon. We'll talk about these and other projects, including the Mars rover. We'll get some insights into the culture of space exploration and also discuss the practical benefits to people here on Earth. We're going to start with a video of the Kepler mission, courtesy of NASA, and then we'll come back and discuss it. So let's go ahead and roll that tape.
We have an innate curiosity about our origins. Is life in our galaxy common? Does it exist? Are we alone? How unique is life here on Earth? The Kepler mission is one step in answering that question.
The Kepler mission is a huge step forward in answering the question, what is our place in the universe?
The Kepler mission is NASA's first mission capable of finding Earth-like planets orbiting other stars in the galaxy in a region around the star we call the Habitable Zone.
The Habitable Zone is where we think water will be. If you can find liquid water on the surface, we think we may very well find life there. So that zone is not too close to the star because it's too hot and the water boils, not too far away where the water is condensed and ice-covered, planet covered with glaciers. It's the Goldilocks zone. Not too hot, not too cold, just right for life.
The primary science goal of Kepler is to answer the question if Earth-like planets in our galaxy are common or rare. Kepler is going to detect planets via the transit method. What we aim to do is to measure the brightnesses of stars very, very accurately for a very long period of time without blinking, so that when the planet passes in front of the star, the light output from the star is going to dim just a little bit. That star is going to blink for about 12 hours, and we will be able to measure that dip in brightness. And it's that dip that we call a transit.
Kepler is a different animal from the Hubble Space Telescope or the Spitzer Infrared Telescope because it doesn't take pictures. You won't see beautiful images that you see from Hubble because we're not doing that kind of science. Those types of missions like Hubble and Spitzer are designed to focus on specific targets.
If you hold your hand at arm's length with a grain of salt or a grain of sand, that's about how much of the sky you can see with a normal astronomical telescope at any one time.
Kepler has a field of view that's 10 degrees by 10 degrees.
Our field of view is about as big as your hand at arm's length, covering the sky.
So rather than taking pictures of very concentrated parts of the sky, we're looking at taking a very broad snapshot of a lot of stars.
Kepler takes really fuzzy pictures. But the thing that Kepler is designed to do, and it does very well, is look for very small variations in the brightness of the stars.
An Earth-like planet passing in front of a Sun-like star is going to cause the brightness of that star to dim by only 1 part per 10,000. That's like looking at a headlight from a great distance and trying to sense the brightness change when a flea crawls across the surface. But the Kepler instrument is designed to detect such small changes in brightness.
The Kepler sensors are CCDs. The CCD in your camera is about the size of one of your small fingernails. The CCD chips on Kepler are a couple of inches square in pairs, and there's 42 of those. In your camera, you might have a few megapixels. If you have a really nice camera, you might have 10 megapixels.
We have 96 million pixels, and they have very low noise, so we can find very small planets.
Once Kepler is launched from the Earth, it will go into what's called an Earth-trailing orbit. Astronomers call that a heliocentric orbit, which means sun-centered orbit.
It looks at the stars continuously, day and night, 365 days a year, and it slowly moves away from the Earth, orbiting the Sun by itself.
And from there, it will point itself at the Kepler field and stare at the Kepler field nearly without blinking for 3.5 years at least, maybe longer if we have an extended mission.
That was our video of the Kepler mission, and now I'm talking with Bill Borucki, who is the driving force behind that mission. Now, I think that video was put together before the Kepler mission was actually put into space, but it actually is in orbit right now, is it not?
That's right. It's been in orbit for about a year now, so we have about a year of data.
And have you found what you're looking for?
We've certainly found planets, and we've found several hundred candidates. Many of them are quite small, toward the size of the Earth, but they're candidates. You've got to look at them very carefully, make many different kinds of measurements to make sure that you're not being fooled, because lots of things look like a planet. If you have a big star and a small star across the big star, you think it might be a planet. So there's a lot of ground-based work that's done after we come up with these candidates, these several hundred candidates, as we show which ones are really a planet and which ones are not.
Now, once you determine that it's a planet, what else can you tell about it? For example, can you determine surface temperature, whether it has air or water or other useful things?
We can tell quite a bit about the planet. First of all, we get its size. For the bigger planets, we actually get its mass. We get its density. We can tell you whether the planet is sort of a fluffy planet. We found some planets that are less dense than Jupiter, some planets, in fact, that have a density of styrofoam. Giant planets with very low densities. We're working our way from the big planets to the small ones, because it gets more and more difficult as you go from big planets to small ones. And similarly, if you're trying to find planets in a habitable zone, then you've got to see them when they have long period orbits. The Earth takes a whole year to go around the Sun. We have to wait about 3 years, so we need 3 transits before we say, yes, we found something, let's verify it from the ground and announce it. So up to now we have announced about 5 planets. They're short period planets, and they're giant planets. This coming year we're making our observations to qualify these candidates. We expect to find planets quite a bit smaller than Jupiter, maybe some that are super-Earths.
Now, let's say you discover planets that are Earth-like. Is there any follow-up? I mean, they're still so far away we could never get there unless we have radically improved means of propulsion.
Well, that's right. Certainly, it's, we're in a stage where we're still learning to develop new space propulsion systems, and people like Tony may talk about that, in fact. So we're developing new space systems, but most of these stars are very, very far away. What we're trying to understand is not about the nearest stars, but about stars in general. Are there lots of Earths? If we find hundreds, and we expect to find hundreds, that means there are lots of places for life. There's probably life throughout the galaxy. If, on the other hand, we don't find any, we have the capability of finding many, then we might be alone. That'll be the end of Star Trek, of course.
All right, so we'd have no purpose, but, well, maybe we'd have the whole place to ourselves.
Yes.
But this is a really complicated project with very little margin of error. What would you say is the most difficult thing about putting together the Kepler?
There's so many good possibilities for missions. We need to know so much about space. Kepler has to be so much better than other missions that people believe it will work well, and it will give them a breakthrough in our knowledge of our galaxy. That's what's required.